Okay, basic electricity, resistance, and Ohm's law. What does the little stick figure here represent? It's pushing those electrons. Well, you could have answered that in a couple of ways. You could have said that that represents the voltage, which is what the person on the video says it represents. Or if you wanted to go a different way, you could say that that represents the chemical reaction that forces the electrons to one side of the battery. Because remember, in a battery, what happens is they position the chemicals in certain areas so that as the reaction happens, electrons get moved this way. Okay, so these are my electrons, and they all get moved down here. So what you end up with is an excess of negative charge down here, which is going to repel all the electrons in the wire. And you end up with an excess of positive charge here because as these electrons were moved, their protons, their nuclei stayed behind, and so you end up with an excess of positive charge over here because they don't have their electrons anymore. Okay, and that positive charge will then attract the electrons from the wire, and so it's really a pushing and pulling force. But if you just answered voltage, that's fine as well. Number 9, when an LED was connected to a large voltage of 7.5 volts, the current was way too large and the LED blew up. From your answers to A, you can deduce, so as the current was, when the voltage was large, that meant the current was also large. Is that a direct or inverse relation? That's a direct relation. As one is bigger, the other is also bigger. So current is directly proportional to voltage. That means as voltage increases, the current also increases. You can imagine if I had more negative charge built up on this side, it would be more repulsive to those electrons. And if I had more positive charge built up on this side, it would be more attractive to the electrons. And so the electrons would move faster within the circuit. And that would be what would be a larger voltage. Which mathematical statement is true? Remember, this symbol means is proportional to. Okay, and as voltage increases, current increases. Is that true? Yes, it is. So this is our correct statement. This is the one which is true. If you make that pushing, pulling force smaller, or sorry, bigger, the current's not going to get, what? The current's not going to get smaller. Yeah, like I said, brain not awake. Which of these represents the relationship between current and, ooh, that should say voltage, not resistance. Voltage. I gotta go fix that in the document. Okay. So as voltage gets bigger, the current also gets bigger. The current is going up as the voltage is increasing, and so it's going to be this one right here. That is the graph of a direct relationship. Okay, thank you, Windows Defender. That's lovely. Okay. What do we call this device that can control the flow of electricity, speed it up or slow it down? Now this one looks a little bit different from the one in the video, but hopefully it was close enough. This is a resistor, okay? And its only job really is to resist the flow of current and to slow the current down. Because remember what happened with our LED back here, right? When the LED was connected to a large voltage, we had a large voltage, the current can get too large. And sometimes, you know, you'll be using a 1.5 volt battery and that'll be too much for your little old circuit. And so you'll need a resistor to slow down the current. Okay, in a metal, the electrons jump from atom to atom like a giant conga line. As this one moves to the right, it repels the next one, and this negative electron repels the next one, and they move along like a little conga line. As one moves, so does the other. But in reality, this process is not 100% efficient. Okay, and the copper atoms in the wire are always vibrating around just a little bit, and you can see the vibrations here, yes. Okay, and what will happen because of that is maybe an electron will get kicked this way every once in a while, yeah? And so you're not always going to have those electrons moving in a single direction just because they're getting moved around by the jostling of the copper atoms. And that's because the copper atoms have heat energy. Heat energy is just, it's the motion of atoms within a substance. It's the motion of atoms in a substance. Okay. Now, when electrons try to move through the wire, sometimes they will crash into an atom, okay, or bump into an atom, and that's the way the flow of current gets resisted. And even if one was going this way, it could still, like, bump into um, the neighboring electron that just didn't manage to move out of the way in time, and it could get bounced back a little bit. And so that's also resistance to the flow of current. And when this happens, some of the movement energy, what's the word for movement energy? That is kinetic. Some of the kinetic energy of the electrons gets converted into heat. Okay? And this is how the electric heaters and the incandescent light bulbs work. Okay. Not only metals have resistance, in fact, metals have the least resistance of most substances. Resistance can simply exist from the fact that some materials don't have a suitable arrangement of atoms for the electrons to flow through. Now, you might be like, okay, well, this looks like a wire still, and that's because this model is not awesome. Say I actually had a wire, but it was full of CO2 molecules. I've got COO, I've got a whole wire full of these, and you'd have to pretend I've drawn a whole ton of them because we don't want to sit here and watch me do this forever, okay? And the thing about carbon dioxide molecules is that they are bonded covalently. All of the electrons in nonmetals and covalent compounds, and actually in ionic compounds and in compounds, all the electrons are locked onto their home atoms. All the electrons are locked onto their home atoms, and so it just doesn't make for a good flow. Okay? And some materials don't have enough free electrons. Well, that would be like the ones we were talking about. I think maybe I got ahead of myself, but that's okay. Just in general, you just have to know that certain things have free electrons that can move easily between atoms and certain things don't. And it's the metals that do have these free electrons, and anything that's not just a metal does not have these free electrons. And certain metals, just because of the arrangement of their atoms, maybe they pack a little bit differently into the structure. Some of them will resist electricity more, and some will resist electricity less. Consider the three factors that affect resistance from the first video. What were those three factors again? They were the resistivity, they were the length of the wire, and they were the cross-sectional area of the wire. Which of these factors is being described in 14a and b? Well, 14a and b, that would be the resistivity. Some property of the material itself just makes it harder for electrons to move within it. Okay, what is the unit of resistance? The unit of resistance is the ohm. Okay, and what is the abbreviation for resistance? It is the letter, oh, that's a terrible drawing. It is the Greek letter omega. This is a capital Greek omega. Capital Greek omega. Omega for ohm. Okay, write the formula, and remember for the formula, we use symbols, the quantity symbols. Write the formula that relates the three electrical quantities shown in the picture to the left. Well, there's three ways you can write it. I'm going to write it in the way that kind of makes sense in this diagram, and that is that the current is proportional to the voltage. So current would equal the voltage, but it would also be, it's inversely proportional to the resistance. So I is equal to V, which is directly to proportional to. So as V gets bigger, you can see in this equation, if I made the top part bigger, the current would also get bigger. If I made the resistance bigger, well, this number is divided by resistance, so that would mean that the current would get smaller. Okay, so that's one way you could have written it. You could also have written it as V equals I times R. That's the most common way you'll see the formula written. Or you could also have written it as, well, let's solve this one for R while we're here. So I need to have R on the top. Maybe I'll do this in black. I is equal to V over R. I could multiply by both sides by R to get R on the top. Okay, there we go. So now I have V equals I times R, and I want R by itself, so I could now divide both sides by I. So that means then that R, those cancel, whoops, is equal to V over I. Okay, what do each of the letters in the formula stand for? Well, V stands for voltage. R stands for resistance. And I stands for the intensity of the current. Okay, what unit is used for each of these quantities? Well, for voltage, we use the volt, which is abbreviated V. For resistance, it is the ohm, written with the symbol omega. And current, hopefully we know this one, is amperes, also known as amps. And the abbreviation for that is A.